going? Yep. Okay.
All right. So let me get this one out of here. Should have that already. There's some dead air in this recording. F14. We might be able to get through 14 today since the exam finished so early. And it's good that they feel like you understand equilibrium, because we're going to come back to that topic in these chapters.
Okay. So do we have a midterm test?
No.
Okay.
I think this is midterm week, isn't it?
Yeah, so technically that was our midterm.
Yeah.
Okay, great. That makes me feel so much better. I did real good on that test then.
It just doesn't count any more than any of the others. Oh, no wonder it's not showing. There we go. Now, there we go.
All right. Let's see. Still getting the glare.
I think the lights from the back of the room get glare. Uh-huh.
That's weird. You would think these are the glary ones, but not the ones in the back.
That's because when you turn the front lights on, only one set's turn on.
Yeah. Or it could be the angle. Okay. I don't have time to make a fine adjustment, so let's go with it the way it is. It looks like it's overlapped a little bit.
Oh, it'll be okay.
Yeah. Okay, acids and bases.
Over the years, the concept of acid and bases have been bandied about.
But the first person who tried to make some sense of acids and bases was a person by the name of Arrhenius. And Arrhenius' concept was that acids produce protons, okay? Because hydrogen is one proton, one electron. All you have to do is strip an electron off of it, and you got an H+, which is essentially a proton. So that's an acid, according to Arrhenius. And this is a base, something that when it goes into solution, these are, we're all intents and purposes, we're talking about aqueous solutions. So an acid will produce protons in solution, and a base has hydroxyls in the molecule. So for example, this one would be, say, hydrochloric acid. So when it goes into solution, it produces that plus that. And these, of course, are aqueous. An example of this one would be sodium hydroxide. So in solution, that would dissociate, and this would be produced. And for most acids and bases, bases in particular, this definition works. But there are some compounds, when you put them in solution, they produce basic solutions. That is, they have the same characteristics as a base. We used to be able to taste the stuff, you know. Bases taste bitter, acids taste sour.
I don't feel like I would have taken.
But we're not, no, we don't do that anymore.
Wait, they tested these, tasted these?
You could, yeah, if you were pretty sure that it was a dilute solution, you were safe enough.
One that wouldn't kill you, how would you know before, after you tasted it?
No, they didn't make students do it. And other characteristics like bases would feel slippery on your fingers. And the conventional wisdom there is that the base saponifies the fats that are on the surface of your skin, and make soap. And everybody knows that soap is slippery. Anyway, this was Arrhenius definition. But there are some, particularly for bases, there are some compounds that will produce basic solutions, but they don't have hydroxyls in the formula. For instance, if we take ammonia gas and put it in water, it produces a basic solution. It does that. Okay? So the end product is something with a hydroxyl in it. But the compound that you form the base, that forms the base, does not have a hydroxyl. So we need to modify the definition. Instead of, for acids, now we're going to, this comes years later, Bronsted-Lowry proposed that an acid was a proton donor, something that gives up a proton. So it still satisfies the Arrhenius concept of an acid because it donates this proton that's available. But a base now, according to Bronsted-Lowry, is a proton acceptor. Right? So under this definition, Arrhenius falls apart. Bronsted-Lowry model will not work with the Arrhenius definition of a base, but it will work with certain bases that Arrhenius would not work. So in this case, this would be, if it's a base, it has to be a proton acceptor. Right? So if this is a proton acceptor, we take one of these protons, put it over here, and that gives us this, NH4. And the proton that leaves here gives us an OH left over. So you have that. And then, of course, in solution, it produces this plus this. Okay. But the reaction we're interested in is this one. Okay? So according to Bronsted-Lowry, anything that accepts a proton is a base. All right. So Arrhenius definition is not used anymore. It's a that's just a historical artifact. We're more interested in Bronsted-Lowry. So we'll focus on that one. So according to Bronsted-Lowry, when you put hydrogen chloride in water, you get a reaction in which the proton donor here is the acid, and water becomes the base. So now we're talking about acid-base reactions. So this acid reacts with that base. Usually don't think of water as a base or an acid, but it is. In fact, it can be either one depending on the circumstance. So we transfer a proton over here. This is the acid that gives it up. This is the base that accepts it. And what do we have left over? We have this plus this. And this has a special name. It's called hydronium ion. Now you're going to see in acid-base reaction equations, you'll see lone protons floating around in the equations. That's for convenience. It works, it gives us the right answers, but just recognize that lone protons never exist. They're always attached to something. So in reality, this hydronium ion is the true species. That's where the proton resides when it's transferred. It just doesn't hang out there. Like I wrote it before, where HCl dissociation to H plus and Cl minus. That's for convenience. That H plus actually is attached to a water molecule. It makes the hydronium ion. Okay. So this is the molecular model of proton transfer. We have water, and we have ammonia that's being attempted to put it in solution. And we form this hydrogen bond. And if it's strong enough, the proton from water will be transferred to the ammonia molecule and make the ammonium ion. Notice that proton is never by itself. It's always attached to something. The same thing can happen to water. If you have pure water, and one of them can become the acid by transferring a proton to the other one. And these are two different molecules. It's not the same molecule. You can transfer one proton to this one, and that leaves that one plus this one. Okay? And that does happen in water. Okay. Oops. Let's see, I missed that. So let me do it manually here.
The Bronsted-Lowry concept defines acids as proton donors and bases as proton acceptors. In the reaction of aqueous hydronium ions and ammonia molecules, the hydronium ion acts as the Bronsted-Lowry acid and the ammonia molecule as the Bronsted-Lowry base. The net effect is that of a proton transfer from hydronium to ammonia, forming water and the ammonium ion.
Okay, now in that scenario, we're reacting ammonia in solution, and because we've already transferred a proton from one water molecule to the other, we have some of these available, the hydroniums. So in that case, this becomes the base because it's the acceptor, and this becomes the acid. So we transfer that proton over here, and that gives us the ammonium ion and leaves behind the water molecule there. Now, let's see, I don't want to get ahead of myself, so let me check my. Yeah, it's the next slide. Okay, this is a generic acid right here, where you have this one proton out front and then whatever else is attached to it. So that's what the A means. It could be anything. It could be a chloride, it could be bromide, it could be nitrate, it could be sulfate, hydrogen sulfate actually. It could be acetate. Could be acetic acid, the one that we're going to use next week. So I need to hand that out to you before you leave today too. So we can do the Ka, and I have to define what that is, of acetic acid for our lab next week. But since I've already got this up here, let's say we have, this is our acid because it's the proton donor, right? This is the acceptor of the proton. Then on the product side of the equation, the proton donor, or the acid, produces a base. And this is actually the conjugate base because it's derived from this acid. Every time you transfer a proton, you produce a conjugate something. So this acid produces a conjugate base. This base produces a conjugate acid. Okay? That just means that on this side, that molecule was a proton acceptor. Now that it has that extra proton, it can be a proton donor. Okay. There's nothing spectacular about this. It just, this side is acceptor, that side is donor. So that means this side is base and that side is acid. Okay? That's all that means.
Acid ionization in water is an equilibrium reaction. Acetic acid ionizes in water to a small degree, forming hydronium and acetate ions. Because of this small degree of ionization, and because water is nearly a pure liquid, we rearrange the equilibrium constant expression. If we now remove water from both the chemical and equilibrium equations, we get the acid ionization constant for water. The Ka for acetic acid is 1.7 times 10 to the minus 5. The animation sequence shows acetic acid reacting with water to form hydronium and acetate ions.
How did I get that far? Okay. Acid ionization equilibrium. Okay, okay. I'll just have to, I feel like I need to say some things about it.
At equilibrium, both the forward and reverse reactions proceed at the same rate, such that the net concentration of each ion remains constant.
Okay, so now we're jumping into equilibrium with acids and bases as our dance partners. They used acetic acid for the example. So here's acetic acid. All right, there's the acetate ion, and then the proton that dissociates from it. Right? So in water, acetic acid reacts with that water molecule, and we set up an equilibrium because this does not react completely. It only partially reacts with water to produce a product over here, C2H3O2 minus, right? There's aqueous. There's aqueous, that's the liquid. Plus the hydronium ion. Okay, and we'll call that aqueous. All right, so the equilibrium, as we wrote it here, is predominantly on this side. It produces just a little bit of this and that. So we can write an equilibrium expression for this one. We just take the product, concentration, at equilibrium, hydronium, and divide it by the equilibrium concentration of the undissociated acid and water molecule. And this is balanced with coefficients of 1 for each one. So each one is to the power of 1. That simplifies things. Now, remember our convention. When we write an equilibrium expression, if there are any pure substances, solids, or liquids, they go out. Gases and aqueous, we can hold, we can keep those. But this is a liquid, pure liquid. That one is removed from the expression, and the only thing you have left is this aqueous concentration, aqueous concentration, aqueous concentration. Those three. And this is one of those Ks that has a special subscript, just the Ka, because it means the equilibrium constant for the acid dissociation. Okay? Now, very often what you'll see is rather than writing the water in here, we'll just leave that out and just dissociate it to a proton there. And sometimes instead of that hydronium, you'll see a proton instead, right? So we could substitute a proton here instead of the hydronium, and it would still be the same dimension, same number. Okay? It wouldn't be physically true because we know the hydronium is the true species. But for simplicity's sake, sometimes we just put the proton in there. And that represents the hydronium concentration. Oops. Take control again. There we go. All right. Now we come to definitions. What do we mean by strong acid, weak acid? Strong and weak refers only to the degree to which this species dissociates. In other words, acetic acid dissociates very little to produce just a few of these and a few of those. So it is a weak acid. A strong acid like hydrochloric acid, nitric acid, they dissociate completely. If you know the concentration of your of hydrogen chloride that's in solution, you automatically know the concentration of hydronium ions or protons because it dissociates completely. So they're equal. That is a strong acid because of its dissociation. It dissociates completely, makes it strong. If it dissociates a little bit, makes it weak. And there is a continuum in between, of course. Now, that's opposed to the concept of, oh, if I stick my hand in this strong acid, it's going to eat it off. Well, if the concentration is only 10 to the minus third molar, no, it won't. All it's going to do is find out where your cuts are. Okay? But if a strong acid is at 1 molar or 10 molar concentration, yeah, it'll eat your hand off. Right? So the difference between what effect it has, its corrosive effect on tissue or metals, so forth, is a different concept to the, what we're describing as strong versus weak. This is acetic acid. If it's at 5% concentration, you can stick your hand in it. That's vinegar. Okay, 5% acetic acid is vinegar. But if you buy from a supplier glacial acetic acid, which is 100%, you stick your hand in that, and it won't take long before it'll start killing your skin, sloughing off. Okay. So there's a difference between corrosivity and acid strength. Acid strength simply refers to how much does it dissociate. Let's see. So here's our strong acid, complete dissociation. If you know this one, you automatically know that one. Whereas weak acid, if you know this one, you only know a little bit of that one, and that the concentration of your hydrogen ions depends on how much of it there is and its equilibrium constant. Okay, you need to know that. For weak acids, you can't tell what the concentration of the hydrogen ions are unless you know that value, because this is what you want to know. If you know that one and that one, then you can figure it out. But if you know the initial concentration of this one, you know that one, then you can figure out the other terms. And I'll show you how to do that too. We're going to use the ice table again, okay? Only with reference to acids and bases. Okay, So a little qualitative discussion. If this Ka value is very large, what does that mean in terms of acid strength? Right? If this Ka is large, that means the numerator is a large value and the denominator is a small value. Right? So if that's true, then the large value in the numerator says there's a lot of this, there's a lot of product. So the larger the Ka value, the stronger the acid. It's about time. We've gone quite a while without rain. Of course, that's a two-edged sword. Now I got to mow the grass. Conversely, if this Ka is very small, like 10 to the minus 1, 10 to the minus 2, 10 to the minus 6, that means that this term up here is very small. The product side is very small, which means it's mostly over here. And that just means that it has not dissociated very much. Very little dissociation. So a small Ka means a weak acid. And the smaller the value, the weaker the acid. Okay. Now, one last thing about the Ka. If this is the acid, the proton donor, that makes this the conjugate base, correct? That's the acid. Once you remove the proton, that makes it the conjugate base. So what does that mean in terms of theory? If it's a base, it's a potential proton acceptor. Okay, so if this is acid, that makes this the conjugate base.
Hey, did you get my email?
Yes. Okay. Yeah, how are things with the youngin?
He's got antibiotics and allergy medicine. They don't know if it's a pink eye or if he scratched it or is having a reaction or what. I got a picture.
Okay. So now we have this acetic acid, and for every acid during a transfer of proton, it becomes a conjugate base. That just means, according to Bronsted-Lowry, that the acid is a proton donor, the base now is a proton acceptor. Okay? So, what does that mean in terms of strength? Right? If the strength of an acid is couched in terms of its willingness to release a proton, then that makes this a weak acid, acetic acid, vinegar. Does not give up its protons easily. So it only gives up a few of them. Right? It hangs on to protons very tightly, except for just a few. So that means when you get to the base side, it really wants to be back over here, right? Because it attaches to protons very strongly. So the rule of thumb here is weak acid makes a strong conjugate base. Weak acids give up protons very weakly. It dissociates weakly. But the conjugate base really wants those protons back. So that makes weak acid, strong conjugate base. So related to the Ka, if the Ka is very small, that means you have a weak acid. And that just means that your conjugate base is strong. Now you can write a Kb expression for this conjugate base, but we haven't got to that step yet. So in case you're wondering. All right, so here's self-ionization of water. I showed you earlier. You can have this water molecule acting like an acid and this one acting like a base. or vice versa. In this case, I would say this is the acid. It gives up a proton and becomes that hydroxyl and transfers that proton to this proton acceptor, which makes it a base. And now that it's got that extra proton, it becomes this hydronium. Similarly, if you have pure ammonia, right, and some farmers still use it, like, I don't know if you've ever seen, probably not around here. It's common to use anhydrous ammonia in these big stainless steel tanks, and they pull them behind their tractors. And they feed their crops with nitrogen this way. It's much more cost effective, if you've got the equipment for it, to use anhydrous ammonia to deliver your nitrogen rather than urea or ammonium nitrate, something like that. But if you do have pure ammonia, then one ammonia can become an acid and the other the base. So one's a donor of the proton, one's an acceptor of a proton, and you get the conjugate acid and the conjugate base. Autoionization. The term for that, when you talk about a molecule that can act as both an acid and a base, that's amphoteric. Ampho coming from the Greek word that means both. It can go both ways. Sometimes it's referred to, particularly in terms of acids and bases, as amphiprotic. That is, it can either give up a proton or accept a proton. Now, as far as water goes, if we write that equation for water, right? Both of these are liquids. And then one produces this one plus this one. Or for simplicity's sake, like I was saying earlier, sometimes this is the way the proton resides. It actually is attached to something. That's the physical reality. For convenience, sometimes instead of that, well, no, that works. Let's just leave it at that. So this is an aqueous solution of hydronium ions, and this is an aqueous solution of hydroxyls. Then if we write the K value for that, we take the products times there, divide by the reactants. Okay? So now, by convention, this is a pure liquid and that's a pure liquid. They both go out. They're not part of the expression. So what we have is hydronium concentration times the hydroxyl concentration is equal to some value, and we give it a special subscript, Kw, for water. Now, at around 25 degrees, actually not exactly 25, but that's close enough for student work. This expression, the K value for the self-ionization of water, is 1.0 times 10 to the minus 14. So, what does that mean? That means that there's very little over here. Most of it is here, right? So the ionization is very weak. And because it produces both protons and hydroxyls, it's neutral. It's not acid or base. By the way, if both of these come from a similar source, like one from this one and one from that one, and they yield this, what are the concentrations of those two? They have to be equal, don't they? Because they come from the same place, right? So in order to produce that value, this one has to be 10 to the minus 7, and this one has to be 10 to the minus 7. Because that one times that one yields this one. Okay? So, pure water at 25 degrees will have a concentration of hydronium ions at 10 to the minus 7th molar and hydroxyls at 10 to the minus 7th molar. Now, let's see. Do it on time. All right. So I'm going to leave those there and make some room up here. Just my luck, I'll have to write that out again. So there are three possible situations. With pure water at 25 degrees, this is the situation. Equal hydronium, equal hydroxyls. Okay, that's the neutral situation, where they're both equal. But if we add some protons to that, it's going to induce an imbalance. And in the case where we have more protons than hydroxyls, then we have an acidic solution. Where we have more hydroxyls than protons, we have a basic solution. So let's look at that here. AW equals hydronium times hydroxyl, and that's equal to 1 times 10 to the minus 14. Then if it's pure water, or if we add equal amounts of acid and base, either way, you end up with 10 to the minus 7th here, 10 to the minus 7th here, and that's neutral. But if we add a little acid to it, what does that do to the equilibrium? We add a little bit of this here. It shifts it back this way, doesn't it? To the left. But not all the way. It leaves some of this behind. It shifts until it reaches the equilibrium. So that means it has to consume some of the hydroxyls and leave some extra protons. So in that case, let's just pick an example. Say we increase the hydroniums to maybe 10 to the minus 6. Okay? That's actually quite a bit, because that's 10 times as much, right? Because we're going from minus 7 to minus 6, so that's an increase of 10 times to go from here to here. So what is this going to be, right? In water, this equilibrium must be obeyed. Right? No matter what we do to water, that equilibrium has to be obeyed. So if this is 10 to the minus 6, this has to be 10 to the minus 8. Because that's a constant. If that's a constant, then we cannot violate that balance. So that makes this acidic. What if we went the other direction? Say we divided by 10. And this would be 10 to the minus 8. This would be 10 to the minus 6, wouldn't it? And that would be basic. Okay? No matter what we do to an aqueous solution, that is always the rule. Okay? So, this is what an acid does in water. The acid produces a conjugate base. Actually, this one, it would have been better for them to, color-wise, for that one to be red and this one to be red. But I guess bases are considered blue. So if that's a base on this side, this is a base on that side. So this is the conjugate base of that acid. And this is the conjugate acid of that base. Okay? So for this generic equation, if we take this product concentration times this product concentration, it goes in the numerator, and this reactant concentration goes in the denominator, and water disappears because it's a pure liquid. Besides that, its concentration doesn't change anyway, right? Pure water is about 34 molar, right? So we put a weak acid in there, it's not going to change. So this is the generic expression for an equilibrium constant for an acid. Okay. Now this is for weak acids. Right? If this were a strong acid, what would it do? This would be completely gone, and it'll all be over here. Right? So an equilibrium expression for a strong acid doesn't mean anything. Right? It has no use. Equilibrium is only valuable for weak acids and weak bases. My goodness, I'm down. Making up for lost time.
Apparently.
Okay, so if the equilibrium lies to the right, the value of K is what? Large or small? Remember, if it goes to the right, it's mostly product. Large, right. Okay. And in general, greater than 1. I mean, and that's a pretty good estimate for acids and bases because we're only doing one proton at a time. Right? So the coefficients are usually 1. And vice versa. If the Ka is small, then the equilibrium lies to the left. All right. I'm not sure what this slide is trying to show. I have to read it to see. For this generic equation of an acid reacting with water to produce the conjugate acid and the conjugate base, if water is a better base than A minus, and A minus is generic, it could be anything, but that's what's left over after it loses a proton. Do products or reactants dominate at equilibrium? Well, let's see. If water is a better base, what do we mean by base? A better attractor of protons, a better acceptor of protons. So if water accepts protons better than A minus, then are we going to have more product or more reactant? Yep. Yep. This is going to really latch onto those protons. That puts it over here. And this is going to try to come back, but it's not as good at coming back as water was going forward.
Sounds like we're
My goodness.
So I'm just gonna go with.
and
Does that mean HA is a strong acid? Is it a strong or a weak acid?
strong.
I would think it'd be strong, yeah. Is the value of Ka greater or less than 1?
Greater.
Greater than 1 because it's headed that way. Okay. You guys are on top of this one. Okay. So let's consider a 1 molar solution of HCl, hydrochloric acid. Let's see if we can order these from strongest to weakest base. So we've got this one to deal with, and we've got this one from a weak acid, okay? And this one comes from a strong acid. So remember what we said. If the acid is strong, the base is weak. And if the acid is weak, the base is strong. So actually, we can nail down the ends and then water goes in the middle. So if this came from a strong acid, it's going to be a weak base, right? So this is a weak base, then water in the middle. That is the strongest base right there. Oops. Oh, I thought it was going to tell us. Well, that's the answer. Oh, I see. We're doing more discussion. Sorry. So that's what I just said. Chloride is a very poor base. It doesn't accept protons easily because it wanted to get rid of them pretty quick as HCl, so it doesn't want them back. So based on strongest to weakest, it'd be this way. Okay. So now we're going to look at, suppose, instead of adding an acid or a base to a solution, we add a salt of the base, right? So if we have this as our acid, but that's not what we're going to add to the solution. First, we're going to convert it to the sodium salt of that acid. Then we're going to dissolve it, right? So in solution, we get this anion, and we're going to say this is a weak acid, right? So that makes this a strong base. And now we're going to react it with water. We can do that because we put it in there by itself. Sodium's not going to react with anything. So you're just dealing with this part of the weak acid. So this is a strong base. And what's it going to produce? Well, we transfer a proton from this one. So this is the acid. This is the base. Transfer a proton. We get this conjugate acid from the strong base. So if this is a strong base, what is this? A weak acid. In fact, we already said it's a weak acid right here. And then what's left over? If we transfer a proton out of there, you're left with an oxygen and a hydrogen. So you got the hydroxyl. Okay? And this is the conjugate base. Okay? Which way would the equilibrium lie? That way or this way? This is a strong base, right? It wants to gobble up some protons. It has a very strong attraction to protons because it came from a weak acid. So a strong base means it has a strong attraction for protons, which means going that way. So the equilibrium lies over there. That's wrong. These slides came from the publisher, and I took a look at that and said, wait a minute, that's wrong. Based on this scenario, it's on the right-hand side. So whoever made the slides got it wrong. So we can write a KB expression for this. So we have the conjugate acid concentration at equilibrium. We have the OH minus, the hydroxyl. We have the reactant side, like that. And that doesn't count because it's a pure liquid, right? So that's our Kb expression for this conjugate base of that acid. So that means this is going to be big, that's going to be small, so it should be greater than 1. And they got it wrong again. So I had to correct it. It's greater than 1. I didn't have to do that, I just felt like digging. Okay. Let's see. Does this mean A minus is a strong or a weak base? Well, of course. If it wants to go that way, it has a strong attraction for protons, which sends it over there. That means A minus is a strong base. Okay. How we doing on time? 2:45. See then if you want to go. Let me get into some of this so we don't have to rush around next time. Acetic acid, and what's HCN? Remember, it's got go back to your nomenclature. Deep in the deepest, darkest recesses of your mind. There's no oxygen, so you start the name with hydro. And cyanide, I's become X, so it's hydrocyanic acid, HCN. And of course, HC2H3O2 is acetic acid. All right, so the question is, if we have these two, and they're both weak acids, acetic acid is stronger than HCN, which means acetic acid wants to dissociate, give up a proton more readily than HCN does. So if acetic acid is there, and HCN is here, then what do they produce when they dissociate? So they produce this one. I'm not writing out the full reaction. And they produce this one. Okay, so if they're both weak, but this is weaker, right? Weaker, that means this is strong base, but this is stronger base. Because it's a weaker acid, makes a stronger base. Okay? So now we can talk about the relationship. Well, also there's HCl. But that produces there. That's definitely the weakest base. So, weakest to strongest. So the weakest base is going to be this one. Okay? The strongest base is going to be this one. Now we have to decide, where does water fit in there? Well, is water a weaker or stronger acid than acetic acid? Right, it's a weaker acid, so it's a stronger base. So water should be over here to the right of acetate. Right? So this is weak, stronger still, strongest. Okay, you follow the logic? Okay. That type of logic will fade fast, so the first opportunity you get, go over it again. Oops, didn't say. Oh, we're going through the logic. Okay, the other way you can approach this is the K values. Right? So this one's going to have K, well, K doesn't mean anything here, but a K for water is 10 to the minus 14. This is like 10 to the minus 5th, I think. And this is like 10 to the minus 23rd, something like that. Weak acid. Okay, so there's the order. Wait a minute, why did it put water first? It put water ahead of acetic acid. I don't think that's right. Because water as a base no, that's wrong. Water, these two should be swapped. Because acetic acid is a stronger acid than water, so that makes it a weaker base. So it needs to be to the left. So I need to make a note of that. They got that one wrong too. Okay. A note for the future. All right. So now that we know how to write K expressions for acids and bases, we're going to allow a reaction to occur in which we have hydrocyanic acid and fluoride ion, right? So how do we get fluoride ion in that solution? Probably something like this, right? Sodium fluoride. Sodium is not going to react with anything. Fluoride is the important species here. So once we get it in a solution, we have hydrocyanic acid in solution, and we mix in some fluoride. And we want to know with this reaction, because fluoride is going to accept the proton and give you the conjugate base of hydrocyanic acid and the conjugate acid of this base, fluoride ion. So we want to know what is the K for that reaction. Okay, remember when we combined reactions? Hess's law, for instance, when we were doing for thermochemistry, right? So we want to look at what reactions are involved. Okay, these are the Ka values for each of those acids. This is the Ka for that acid. This is the Ka for that acid. Okay. So there it is restated. What does each Ka mean? Well, it's a dissociation. You have the acid on the left and the conjugate base on the right. Right? So for this one, Ka is small for HCN. Actually, I was wrong. It's not 10 to the minus 23rd, it's 10 to the minus 10. Which equals a strong drive to keep it as HCN. Okay, that's the first point. Most of it's going to be HCN over here. The Ka for HF is small. Not as small as HCN, but small. So it's going to be a strong drive to make HF, right? So if this strong drive to make HCN and this strong drive to make HF, which is the stronger, right? Which one wants to keep their acid form? Well, the one with the smallest Ka is going to be the one that wins, right? So the HCN wins, and most of it is going to be on this side over here, because the drive is for HCN, which has a very small Ka, to be there, rather than for HF to be there. That's the first point. Comparing those Kas tells you which one should dominate, HCN. Okay, so left toward reactants is where your equilibrium is going to lie. And that just means, without actually doing the calculation, you can give a semi-quantitative value. It's going to be less than 1, right? Because if we're favoring this side over that side, that makes this small and that large, and it has to be less than 1. Okay? Now, suppose you know the Ka for a weak acid, but in order to use the K in a combination where you add equations together, or where you're looking at an equilibrium where you're not dealing with the acid like HF, but you're dealing with F- as your starting point. Right? If that's the case, then you need to know Kb, where it reacts with water, not Ka, because F- is the one that's reacting with water. So you need to know the Kb. So if you know the Ka, can you find the Kb from that? Well, it turns out, yes, you can. But it's not a simple, it's not an intuitive process. Let's put it that way. You need to justify it by calculation. So if here's the weak acid, and we know the Ka, it produces this species, whatever it happens to be, plus the proton. Now in this case, we're using protons instead of hydroniums, but the end result is the same. So there's your Ka for the weak acid, right? So these are going to be small. This one's going to be large. And what we're doing is we're reacting this species with water. That's the Kb. So the Kb expression is this one, Ha over times OH divided by A minus. Okay. So we need to do something to transition this one to that one, the one we don't know. So what happens if we add those two together? Well, look, this one's on that side, this one's on that side, so they cancel out. Okay, this one's on that side and that one's on that side, so they should cancel out too. All right, so what does that leave us with? It leaves us with water on this side and hydrogen and hydroxyl on the other side. Okay, that look familiar? That's water dissociation, Kw. So when we add Ks together, what do we do to them? We don't add the Ks, we multiply the Ks. Remember that from equilibrium. If you add two equations together, you multiply the Ks. So when we multiply, and that should be a dot or an X, when we multiply these Ks together, they have to be equal to the K for this one, which is Kw. So Ka times Kb equals Kw. That's the secret. If you know Ka, and of course you know Kw, 10 to the minus 14, then Kb is just Kw divided by Ka. So there you go. Kw divided by Ka gives you Kb. vice versa. If you know KV, you just divide it into 10 to the minus 14. It gives you KA. Okay? So I believe that one's should be in useful information. Let me check to be sure.
Everybody get a copy? I must add some extras.
Yeah.
We need those 14 in, right?
Yes. Yeah, we're gonna get to 15 next week. Yeah, where is it? There it is. It's written in terms of KW equals KA times KV.
That way, you can just solve for the one you need. So if you have one, you can find the other. Calculate the value for K for the reaction. Okay. Now we're going to actually use those values here, right? And calculate the K for that reaction. Okay, so we have two competing dissociations. We have this one producing hydrogen and cyanide, and we have that one producing hydrogen and fluoride. Okay, so the Ka for this one is that times that divided by that, and there's the value right here. And then this one will be that one, products divided by reactants, and it's equal to that value. Okay, so now, the thing is, this says that F minus is on the right-hand side, but actually F minus is on the left-hand side. So we need the inverse of that. So this reaction needs to be inverted so that we can get F minus on this side and HF on that side. Okay. So from our previous slide, we know that this is actually KB. And KB for that expression is, well, now that's not exactly right. I say it's KB, but that's not the way we wrote KB before. We do need the inverse, that's true, but I hesitate to call it KB. I would just say K. Because when we add this one together with that one, we should get this one, right? That's the first law. You have to be able to put them together and make this. So there's HCN, right? There's F minus. We got hydrogen on this side and hydrogen on that side, they cancel. So there's CN on the right and HF on the right. Okay, so that's fine. So we inverted the equation and wrote this one out. And when you invert an equation, you can take the inverse of K. So that's what we did here. And leaves us this value. So now when we add them together, then we multiply this one times that one. Let's see. Right, that's when I added the two equations together to give me this. So now you cancel the hydrogen ions that are on both sides. And there's your finished equation, which is equal to the one we started with. That's our target. And then the K for the reaction is multiply these two together. And you get 8.6 times 10 to the minus 7. Okay, pH. You guys use pH in before this class, or maybe in MLT? Okay, so you have a practical working knowledge of pH. pH is simply the negative log of the hydrogen ion concentration. And that's what Sorensen came up with, that as a more convenient way of dealing with these huge numbers, right? Like 1.5 times 10 to the minus third molar hydrogen ion concentration. You just take the negative log of it and you have a simplified number. So what it means is as the hydrogen ion concentration gets smaller, it's more negative power of 10, 10 to the minus third, 10 to the minus fourth, 10 to the minus fifth. The negative log gets bigger. So the larger the pH, the more basics of the solution. And the smaller the number, the more acidic the solution. It's just inverse. Okay? So if we do that to pure water, where the hydrogen ion concentration is equal to 10 to the minus 7 molar, then the negative log of that whole expression gives us negative log here, gives us pH, and the negative log here gives us, what's the log, the common log of 10 to the minus 7? Right? It's just the power of 10. But we got a negative, so we need 7. So neutral solution is pH 7. And based on this, if the concentration increases, 10 to the minus 7, 10 to the minus 6 would be more concentrated, 10 to the minus 5th would be more than that. Then we take the negative log of that, that makes this number smaller. So 6 is more acidic than 7, 5 is more than 6, and 4 is more than 5. Okay, smaller number. And the other direction for the basic solutions. Those are just some examples. I think the normal for blood is like 7.35 to 7.45, I believe is the buffer region for blood. If you get too much, you get too far beyond that, either acidic or basic, you're going to be sick. If you go far enough, you'll be dead. Okay. Calculate the pH for each of these. Right? The first one is easy because it's 1 times 10 to the minus 4. So the negative log of that of this, how do you do logs? If you have a log of something times something, it's the log of that plus the log of that. So the times becomes a plus. So it's the negative log of 1 plus the negative log of 10 to the minus 4. Okay. So what's the log of 1? 0. And this one is 4. Okay. So the pH of that solution is 4. How about the pH of 0.04 hydroxyl? 0.04 molar hydroxyl. Well, there are a couple of ways you can approach this. One is you can convert that to hydrogen ions. Remember, 10 to the minus 14th is our K value, and that's equal to hydrogen ions times hydroxyl ions. So that means hydrogen ions times 4 times 10 to the minus 2. Okay. So then you would say hydrogen ion is 10 to the minus 14 divided by 4 times 10 to the minus 2. And then you take the negative log of that. Okay, that's one way to do it. Let me see. Should be coming up here pretty soon. Quicker way. Yeah. Well, if we did that, let's just do it that way. We ought to do it the hard way at least once. So we're going to take 10 to the minus 14 divided by 4 times 10 to the minus 2. Okay, and 4 exponent is 2. That's 2.5 times 10 to the minus 13, and that's equal to the hydrogen ion concentration. Then we need to take the negative log of that whole thing. Negative log of this one, negative log of that one. That makes this pH, and change that. That makes this 12.6. So by that method, the pH is 12.6. Okay? Now that we've done it the hard way, let's learn the easier way. Okay. That did it the hard way. Now we're going to do it the easy way. Remember that Kw equals hydrogen ions times hydroxyl ions is equal to 1 times 10 to the minus 14. So what if we took the negative log of that entire expression? Kw equals this one times this one equals 1 times 10 to the minus 14. And we're going to take the negative log of the whole thing. So the negative log of this one is a new expression called pKw. We're just using Sorensen's convention. Negative log of anything is p something. So pKw is this one. And then negative log of that one is pH. And remember, log of something times something is value plus value. So pH plus POH. Okay? And that's equal to negative log of this one is 14. Okay? Look at what that means. If we find the POH, just subtract it from 14 and you get the pH. So the pH is equal to 14 minus POH. So we could have done the POH of that value 0.04 and just subtract it from 14 and we get 12.6. This just works the whole thing out for posterity's sake. Right? So using those terms, the POH for this one, we found the pH to be 4, and 4 from 14 is 10, gives you POH. Right? So just subtract pH from 14 and you get POH. And then the other one, the POH is 1.4. Right? If we take the negative log of this, subtract it from 14, and you get 12.6. So that's the quick way, the easy way. All right. Oh, I skipped something. For this one, if the pH is 5.85, what's the hydroxyl ion concentration? Let's do that one. Because that actually works backwards. It uses a concept called the anti-log. So if the 5.85 equals the pH, right? And we want to know what's this one. Then we want to find POH so we can back calculate. So what's the POH? Is equal to 14 minus 5.85, which is 514. Nope, wrong. 5.891, and 5 from 13 is 8, right? 8.15. That's the POH. Now, what's the hydroxyl ion concentration? Well, you have to know how logs are calculated. So if we say the log of X equals Y, we need to know the base of the log. In this case, it's 10. This is the common log. So that expression means that 10 to the Y equals X. This is the power of 10 that equals that number. That's what logs mean. So if you have this number is there, then you just need 10 to that power, and you got X. And that's your hydroxyl ion concentration, except we have a negative in front of it, right? So then you just take the negative. Well, actually, here's what you have to do. Negative log of that is, let's do this. OH minus equals POH. So now if we substitute in here, this is 8.15, and this one, like that. So we would say the log of this one is equal to negative 8.15. So then you take 10 to that power. So that's the step that you don't want to mess up. That negative needs to go over here before you do the anti-log. And on your calculators, the anti-log is 10 to the power. It'll be 10 to the, usually you'll have a log here, and then a function key above it will be 10 to the power. You just have to be sure and put that negative in there. And that'll give you OH minus concentration, and there it is. We run through that whole situation, take the anti-log of minus 5.85, no, not 5.85, 14 minus 5.85, 8.15. Then you get hydroxyl concentration. Okay, let's see. 315. Okay, we're good till 350. Let me see if this is a good place to break. Okay, so we're going to get into calculating concentrations in solutions of weak acids. Let me see what we got to do next week, if it's going to be short enough. It's basically talking about buffers. You know, we might have to postpone the KA another week, because chapter 15 gets into that in detail. And if we're able to talk about that next week, then the following week, you'll be primed for the KA determination. So let me make a note of that. Let's move the KA lab, which is scheduled for next week, and just shift it down to the 21st of October.
So today we're doing Leslie's study.
Right, we're doing Le Chatelier's today.
And then,
And that one, it doesn't have a formal report.
the next slide will be 2 weeks from now.
Right, on the 21st. And that'll give you, they'll still give you a week between that one and the next one.
And
That'll be good. That'll work out.
3 weeks is the test, right?
Yeah, right, we got this one, this lecture this week, and chapter 15, well, actually the rest of 14 and 15 next week. And then following that, which should be a review, and then another test. So this is a good place to stop, I think. You're welcome to read ahead. You know, I have no objections to that. But I think we'll pick this one up on the 14th.
And we'll take a short break and reconvene in the lab.
I'm not sure if I'm going to put this one up on the, I could put this one up as part 1. And then after we finish it next week, put it up as part 2.
So we're meeting over at the lab.
Yeah, we'll meet in the lab. So let me stop